Just
Okay, so I think what I was worried about, the main reason I wanted to have the quiz at the beginning earlier is exactly what is happening right now. Is I don't have your minds with me, right? Which means everyone is trying to wrap up something in the last minute, right? My advice is don't do that, right? Because it just adds to your stress, and then simply it's already whatever is happened. Assume that the quiz started at the beginning, okay? This quiz is hopefully is an easy one if you were able to solve the exercise problems that we had earlier. So don't pay much attention, because I don't want to keep talking for around like 40 minutes without any benefit, right? So I really hope you leave what you're doing and then focus with me. I might just give you maybe 10 minutes in between before we start the quiz, okay? 10 minutes means let me try to calculate this. So we have up until 12:15. Let's aim for 11:45, and there's a 5-minute. Okay, so we'll just talk for half an hour, okay? And then I will stop. And then hopefully there is some time if you have a last-minute question or if you want to take a break, and then we continue. But this is only under the promise that you leave what you're doing and focus with me, okay?
We have like how many minutes for question? How many minutes for question?
The quiz will be 20 minutes.
So 10 minutes question?
We'll see, yeah. Okay, in fact, there is one thing I wanted to ask you about before we start. It's a logistical thing. Remember last week or on Monday, we said that we need to start preparing for the presentation, right? But then after talking to the other section and thinking a little bit, I'm feeling there is a lot of load of that course. Right? You guys have like project labs and then the quizzes and the midterm. So one thing that comes to mind to ask you about, again, I did not make any decision, and hopefully during this weekend, we'll have all the details, but I'm just soliciting input from you, right? So do you think it will be better for you if we change the presentation to be a presentation about your project? In that case, you come to the lecture, and then you talk about, well, the overall picture, then you try to basically pitch your project to others, right? Why you think it's interesting, it's useful, what you try to do. Now, one point, if you have groups from other sections, I don't know if that's the question that everyone want to ask. If there are a few number of groups, that's okay, because you, again, I never had a constraint about who is attending what, right? So you can shuffle lectures at this point of time. My hope is that that's not a lot. So we will not have one lecture where everyone's attending, the other one is empty, right? Because we'll not be able to finish presentations. But other than this, if there are few groups, this should be okay. Yeah.
Yeah, like taking it from a game theory perspective, the harder the task, the easier it is, the easier the grade will be. So like, if I can do the research with ChatGPT, which is the first then like.
I don't know why you're very obsessed with ChatGPT. So basically, our everyone is not only you, right? But the point is about the presentation. It's not about preparing the slides. It's in fact about coming, standing on your feet, talking confidently and technically correct about stuff you have done, right? Whether this is a paper you read or something you have done yourself, then I'm assisting you not based on the content on the slides, because I know everyone can bring content from everywhere. I'm assisting you based on your own understanding, your answers for the questions, the flow of your presentation, of how you present your ideas, right? These are things that ChatGPT cannot do for you, right? Yes, there is an element about the content itself, about the slides, right? But put in mind that this is a learning component. We are not, I keep saying this a couple of times. We are not at different boats. We are not enemies, more or less, that you guys are trying to bring up ChatGPT or other tools to help you with that. Again, I don't mind this. I do use ChatGPT a lot, right? But I'm urging you to use it the right way, not the wrong way, right? The reason that I'm asking you to presentations is because you go and work for industry or do grad school or whatever, 30% of your time are either presenting or preparing presentations or writing papers. It's all about these skills, right? So I want to add one element to you, gain you more experience. This is what we call like a safe playground, right? This is your backyard where you come talk to your friends. I'm not really, well, you'll not lose a job because of this presentation, right? And you are not going to lose a paper or a master defense because of this presentation. At the end of the day, what are you going to lose? Like 1 mark out of 5, right? It's not going to change your wallet, right? If you did too bad. So think of it as it's a safe trial rehearsal to increase your skills, right? Don't think of it as this is something very stressful. I need to look for other tools and then I'm not capable enough to prepare a presentation. That's not true, right? Use ChatGPT as you would like, but don't replace your mind with a tool that's going to make you worse, right? That's really the whole philosophy about this presentation, right? Again, enjoy it. Talk about whether it's a project or the other stuff. You are learning, right? You are here to learn. I'm not here to basically slam your grades or ruin your future. That's not that, fellows, right? And I will give you feedback as well, how to improve, right? So part of what I have always done in presentations is give you a private feedback on iLearn. That's simply, okay, this part you did great. This part, maybe you need to improve. And it's not necessarily when you say you need to improve, I deduct marks. I only give the feedback. The main purpose is to, in fact, you improve yourself, right? Grades is a second factor, right? So don't always think of, well, I have a lot of feedback that means that I'm losing a lot of grades. Again, that's not the purpose, right? Here, this is an education environment. It's not a judging environment, right? It's not that, well, everything is a great contract. And then, well, I did bad in grades or I did good in grades. I'm genuinely interested in making you a better learner and giving you a technical material, but also at the skills level. And the presentation is one factor of this. Good? Now, going back to the proposal, right? I'm going to ask a question and then please raise your hand if you agree, okay? If you agree to change the presentation topic from the modern topics of embedded system to the project that you have done, please raise your hand. Yeah, if you, okay, so how many, you're raising your hand? Yeah, just your opinion is fine, right? So just put your hands down. Those that didn't raise hands, it doesn't matter for you or you disagree, because both makes a difference. Doesn't matter, okay? Is there anyone that is not happy about, basically you want to do the presentation? Because in reality, I might still, if there are few, I might still give you that option. You can still do it. Yeah, good. That's also a good question. So what is the difference, right? In the presentation, in the lab, it's going to be the demo. You are going to get your project working, and that question, you sit working in front of me and sensibility. And then we're going to ask you technical questions about the project itself. How did you do this? Explain to me this block of code. So it's low-level technical details, right? And running the project. The presentation goal is different. Well, I wouldn't, theoretical might not be the very correct word, but it's more about, the spread of what you're trying to achieve, the logic, exactly. High-level presentation. And by the way, in industry, you usually do both, right? You do the demo at one stage, but early on before the demo, we usually present your findings to others. Yeah.
Let's say hypothetically, if someone got 17 out of 20 in the project, I think that the presentation would be around the same boat.
The presentation is a separate evaluation component, right? So the way we grade the project, even the demo has a separate evaluation component than everything else, and the milestones, right? Yeah, I can share with you a rubric, for sure. Yeah, that's also a fair point. I can share with you a rubric for the presentation. I will ask Sensibility to prepare something for the demo. Yeah.
A week for presentation slide.
Yeah, this is also a good point. I mean, so it depends on how many presentations and the slots we have. That's really my biggest my biggest factor. They will be towards the end, right? At the end of the day. I mean, according to my current plan, and hopefully nothing comes up, because in last lecture I mentioned to everyone that I might be under an emergency situation that I need to cancel 1 or 2 lectures. But assuming everything is okay for this section, hopefully we will be done by the technical material sometime next week, right? And then we can, and we also have the midterm, like putting into account that on Wednesday we'll have the midterm, which means next week is week 11. So most probably the presentations will be week 13 and 14, for example.
Wait, so we're done with all the content by next week?
Next week or the week after. Yeah, because again, we have quizzes and midterms that will delay this a little bit. Yeah. So week after means we're talking about week 12, right? More or less.
We're like almost done with it.
Well, we are at the end of the semester anyway.
No, because like we are like 2/3 of the semester.
Well, that's good in mind that we have a lot of evaluations. Like again, today we're taking half of the lecture for a quiz. Next week we're taking a full lecture for a midterm. We still have 2 quizzes, which means this to me are evaluating to 1 extra lecture as well, right? So that and then we have the presentations, which will take two weeks for this, right? So week 13 and 14 to answer your question. Good. Any other concern, question, suggestion as well? Okay, so again, don't take this that I'm deciding that it will be the project thing. Again, I was just collecting inputs. Again, if you want to share with me something private, also you can email me or come to office hours. By weekend, I will give you all the details about this presentation. Good? Yep.
So what's the answer for the ABC exam?
Yes, I will do. I will do, especially because you need to prepare for the midterm as well. Yeah, I will do also for, I didn't do for the first quiz, but I will do for the first quiz and for today's quiz. Good. Okay, good. So last time, we went into the third shared resource component in our system on a chip, which is the main memory, the DRAM, right? And hopefully last lecture made you appreciate a little bit the complexity of a modern memory control, right? You see that we have grown in complexity between the interconnect, which we looked into it as just a one very uniform resource. You access it once, you take a fixed time. And then we move to caches where we got the problem of everyone is studying the quiz. Okay, how do we handle that? I don't know, like maybe quiz 3 and 4, I should bring it back to the beginning of the lecture, right? That's the only way, right? Until you get done. Again, I understand, right? I mean, there is a pressure on you, like mentally that well, there is an exam component that's coming soon. This lecture I can really care about later. But again, I don't want to keep speaking for no reason. So what about the following? Well, we need to finish this content anyway, so I cannot really postpone, right? I said I promised I will give you this before the quiz, right? But this didn't really help, right?
Yeah, you can do a revision.
So for the midterm, the material is up to the material of the quiz, right?
The midterm is up until today's quiz, which is end of lecture 7. That's correct. From the beginning to lecture 7. Any tangling question in your mind? You have a question? Yeah, well, lecture 7 is more theory because again, there were no practical questions. The main equation of lecture 7, which is the way we decompose the worst case computation time and the interference, plays a very important role for the subsequent lectures, which is interconnect, caches, and DRAMs. We will solve problems about this, which means if you were to receive problems about lecture 7 in the quiz and the midterm, where we don't have the shared resources like interconnect, caches, etc. into account, they will be mainly theoretical questions, like multiple choice asking you about the different 2 techniques of doing worst case analysis, whether it's the static or the measurement based, but there is no numerical question up until now. The numerical questions can make sense once we start introducing the shared resources, right? Good. Okay. Can I ask you again, like for a request, that just take the quiz out of your mind, and then we will have a few minutes. Again, this is we're also wasting time now, so which means we put a pressure on the technical content. But just with me for a few minutes, and then I will give you time. Maybe we'll have 10 minutes to take questions if there is anything open in your mind. Okay? Yep. I'm on. Okay, good. Okay, so continue what we were doing earlier. So we started with the interconnect, which is the simplest form of a shared resource. Why it's very simple? Because once you are granted access to this interconnect, you're going to suffer a fixed time, right? What called S, the slot time. And there are 10 cycles for everyone. Then we introduced caches, which is a little bit more complex because caches introduces hits and misses. So now it's not that I go to the cache and I'm done. I might go to the cache and I'm hit, I suffer some time, but I might miss and go to another resource. This hit miss didn't exist in the interconnect, right? And this is what made caches a little bit more problematic. The reason or the way, well, the reason this came into account, there is a variable in the access latency because I might hit into this level or the subsequent level. The solution we have done, our resources classifying them into hits and misses. Good. Now, last lecture we introduced DRAM. We said the complexity even goes more because the variability is not in whether I'm really accessing the DRAM or not. The variability is even if I'm accessing the DRAM, different requests will suffer different delay based on whether they are raw hit, are raw miss, going to the same bank, going to a different bank. And there is a lot, yeah, it's not truly random access, right? There is a huge variability in the access latency, which what we presented, these are real numbers, by the way, from DDR4, which were presented by this graph, saying that the best scenario is you might suffer 15 nanoseconds to access the DRAM, and the worst case scenario for a single request is going to up to 108 nanoseconds for this DDR4 memory. Good? You have a question?
Just in general, so since it's different and in cache as well, you have hit or miss, it's random, you only know the percentage. Then how do we decide the time again? Like, I can't say that this request will on
From a worst case perspective.
Yeah.
Yeah. For caches, we solve with this by saying if I can classify, then I can really solve the problem for worst case. Because if I know that certain number of requests are guaranteed hits at this level, I'm going to only multiply by the hit delay. For misses, or the ones that I'm not able to classify, they will always be misses, and then I suffer the miss delay.
So I know that this task, when it does this request, it will hit definitely.
Yeah, from your NX.
This specific request or a number of requests?
Well, you do this for every single request, which means if you have a million requests in your task, if you're able to classify that 20% of them are guaranteed hits, then those will be hit rates, right? Yeah. Now for DRAM is a little bit more problematic because if you say I have 100,000 requests going to the DRAM, now I need to do something to say, well, I shouldn't assume. And in fact, some of the existing solutions, I think everyone is suffering this worst case. But that's very, very pessimistic, right? It's thousands of cycles, right? And one very important note that we stopped at the lecture last time is that all this variability does not take into account any queuing or arbitration or scheduling in the memory controller. We are saying that once a request is granted access to the memory, all these variabilities in the access latency. Because remember at the beginning of the interconnect lecture, we said there are two components of latency. You suffer arbitration latency until you are granted access, and then you suffer the access latency. Good? So this is all the variability in the access latency.
This is part of the miss. Like when
this is all if you miss in the cache for sure, right? But here we are studying the DRAM components separately. We are only looking for requests going to the DRAM and we analyze them. And this is the concept we mentioned also at the beginning. We said to simplify our world, we want to take every resource separately, and then we can combine everything by multiple added terms. But and we said there is like around 620% variability window between the best case and the worst case. And my worst case latency is this one, which is 108 nanoseconds. So this is only the access time. Good. Now, we should start even accounting what I miss from the last level cache. So if we go back to the higher level architecture, so you have your CPU, maybe you have your L1 cache, and then you might have a last level cache, and then you have the memory controller, and then you have your DRAM. And we call this is all on a chip, and this is off chip. Now, a request going from the CPU will go through the private cache, then through the interconnect to the last level cache, and then it misses. This is a miss, and it goes to the memory controller, right? All the latency that we had in earlier slides is once the memory controller is ready to send that request to the DRAM, which is the access latency of the DRAM. But in reality, we have to account for the total delay from the time you leave the last level cache, right? So you also have to take into account all the delay you suffer inside the memory controller. Why there is a delay that you will suffer inside the memory controller is because you are not the single request in the system. There might be multiple requests from the same core, from other tasks, from other cores, right? All will be competing with you in the memory controller, right? So if you have another CPU, for example, also missing and going to the last level cache, you might arrive, your request might arrive to the memory controller, your request 5, for example, and then there are 4 requests in front of you in the queue, right? So you will suffer additional delay. We call this arbitration delay at the memory controller, right? What we're going to study from now up until almost the end of the lecture of the DRAM is how to account also for the arbitration delay inside the memory controller. But to understand this, we need to understand how the memory controller, in fact, operates, right? We said that the memory controller does 3 main tasks, right? Last time. Do you remember any of them? Yeah, so scheduling and arbitration, that's the one that we're concerned about today. Yeah, it keeps track of the memory state and accordingly send the right commands, right? Which is command generation. And there is a third one. How do I know? The question that kept, like you asked it, how do I know which request goes to where in the DRAM? What we call the address translation, right? I receive a request, I chunk it into bank, row, column, channel, etc., to target it to the right place, right? So the memory controller does address translation, command generation, and scheduling, right? So command generation and address translation, okay, we discussed last time. Scheduling is the most complex part. That's the real intelligence of the memory controller that simply adds to the complexity, right? So now there are 2 types of scheduling that happen inside the memory controller. There is a one that happens within the same bank and one happens across banks. Good. We call this intra-bank scheduling and inter-bank scheduling. Why this is the case? Because requests going to the same bank will interfere with each other more than requests going to different banks. Remember last time we said banks are more of parallel components. There is minimal interference, but within the same bank, you interfere on the row buffer, right? On the sense amplifier. Usually a memory controller is composed of multiple queues. You have 1 queue per bank, okay? When the requests arrive to you, you push them to the corresponding bank queue. Again, how do I know which queue to push to? From the address translation, right? I get the bank bits. I know you're targeting bank 0, so I put you in the queue of bank 0 or bank 1, etc. Now, within this intra-bank scheduling, most existing memory controller try to optimize for bandwidth and average case. If you think from what we discussed last time, we said there are 3 types of requests going to the memory controller. There is a one that simply hits into the sense amplifier, raw hit. You only suffer a read-write delay, so this is a very fast request. This is your best case. And there is a request, if I go back in the slides a little bit, at this traffic light thing, right? This is your best case, the green one. And the worst one is a row conflict. You come to the memory controller bank to realize that there is a different row than the one that you are asking for. So you are going to suffer more delay. Now, if you were the memory controller or the one architecting the memory controller, and you have a bunch of requests in your queue, some of them are targeting the open row, some of them are targeting other rows. Which one you will favor? Which one you give higher priority? The open row, right? To improve the performance, right? Once I bring in a row from the cells to here in this operation, once I bring in a row from the cells to the row buffer, to the sense amplifiers, I want to maximize the hits in that row. So you use your row buffer as if it's a small cache, right? So if I go back to the queue structure, you might have a bunch of requests in front of like the memory controller in front of the scheduler, and I want to pick the ones that target the current open row to minimize the average time, right? So this is just one possible instance, a scenario just to explain to you the stuff. You look into bank 0. Here I'm referring to C as a row conflict, C as a conflict, and O as an open, okay? Open row or row hit, okay? So O means you are targeting an open row, C you are targeting a closed row or a row conflict. And then RUA is what we call the request under analysis. That's the one that maybe we try, it's an arbitrary request that you want to bound its worst case. Good? Now, the memory controller that is prioritizing open requests over closed one, it deploys a mechanism called first ready, first come, first serve. You know first come, first serve, right? That's simply just a queuing thing. Whoever arrives first is going to finish first, right? But then first ready means, well, I do reordering. I say, no, I don't only serve based on the arrival time. I serve based on whether you're targeting the open row or not, right? So you look into your queue. and then try to pick a request that targets the open row first, even if it arrives later. Like in this scenario, the open ones here are targeting the open row in bank 0, but in fact, they are arriving later, right? Because this is your arrival order. Like if you look into the time, this one arrived first, and this one arrived last, right?
So it's also called first come first serve because it doesn't follow something like a round robin. Or something.
Yeah, why is called first come first? That's a good question. So we discussed the first ready bar, which is I look into my queue and pick a one that targets an open row. Okay.
The first one.
Exactly. Now there are two that targets an open row. Which one do I pick? The one arrived first. This is why it's called first ready and then first come first serve. Now, what if I go to the queue and I don't find any open request? Something like this, for example. What do? You have to pick a one that is close because there is no open anyway. Which one do I pick? There are multiple close. Again, the first one. This is why it's called first ready and then first come first serve. Good. Again, why memory controllers do this? This is, by the way, what is happening inside any machine you would have, right? This is consistent in Intel, in ARM. Every single high-performance memory controller is doing this first ready, first come first serve. So, what was my point? I forgot what I was going to say. Oh yeah, why we're doing this, right? Again, to improve the performance. If you target an open row, you are going to utilize a lot of hits before you close that row, right? If you think about just doing an absolute first come first serve, right? And I have these 5 requests, and I assume they arrive in this order. Like I will give you a sequence of requests. Assume I only have 2 requests and they're doing row 1. Sorry, I have a bunch of requests that are targeting only 2 rows. Row 2, and then row 1, and then row 2, and then row 1. This is request 1, request 2, request 3, request 4, and then request 5. And this is the arrival order, okay? So request 1 arrives first, then second, and third, okay? So now if I do first come, first serve, what is going to happen? They are all targeting the same bank, but they alternate in rows, okay? Row 1, row 2, row 1, row 2. If I do first come, first serve, what's going to happen? Yeah, first request. And by the way, those are typical examples we have in like problems related to DRAM in an quiz or an exam. I give you a sequence of requests and you analyze which ones are hits and misses. So now we are doing first come, first serve. At the beginning, assume everything is idle, right? So this one is a miss, a row miss, which means you need an act and a read or write, right? So I do my read or write and bring row 1 into the row buffer. So this one is a miss. And then, which is simply was our yellow color, right? That's the one in the middle.
We assumed it here, right? We assumed here that row 1 is not ready.
Yeah, at the beginning, we assume everything is idle. Yeah. And then second request is targeting row 2. What do I do? It's a conflict. Yeah, pre-charge, act, and then cast or read, right? So this is a row conflict. You suffer the maximum delay, right? So in this case, you are in fact the red one. Just to give you some numbers, the yellow one with the act and the cast, it might suffer something around, let's say, 15 cycles. Okay, these are also real numbers. The red one is suffering something around 70 cycles. Okay. Yeah, we will see that. So this is a red. And then once I bring in row 2 and I'm done with this request, I go to the one afterwards. It's targeting row 1. Row 1 is different than row 2, which is the one that is currently open in the bank. In this case, it's again a row conflict. So it was going to suffer 70 cycles. Then the same thing, then the same thing. Now, if you count the total delay, you suffer 4 multiplied by 70 plus 50, right? That's quite of a big number, right? It's 140, 280, and then 295, right? You suffer a total of 295 cycles. This is under first come, first serve. Let's see the benefit of first ready, first come, first serve. First ready, first come, first serve says, no, I don't really serve things in the order of arrival. I want to improve performance, right? So what I'm going to do is in the first one, I'm going to open everything to me is like a row idle. So I can pick the oldest one anyway, right? So I open row 1 and I'm going to suffer the 15 cycles similarly. But then afterwards, once this is done, I look into my queue and I find all these requests existing in my queue. Which one do I pick for first ready, first come, first serve? It has to be this one, which is the oldest one targeting row 1. Why row 1? Because it's the one that's currently open in my row buffer, right? In this case, my service order will be request 1 and then request 3. And how much time request C is going to suffer? Let's say a row hit is suffering something like 10 cycles. Okay. And then what is the one I serve afterwards once I'm done with request 3? Request 5, because again, my open row is row 1. Is there any pending request for row 1? Yes, it's request 5, so I serve it. Then request 5 is going to suffer also 10 cycles. Once I'm done, I go to my queue. Yeah. Yeah, okay. So good. So what these numbers I'm giving you from my own experience with DDR4, reasonable things. So I have 3 types of requests. The 15 is the yellow one, right? Which is the one that is in the middle. You need to activate the row and it's idle. This is the conflict one. It's a mess. You have to pre-charge, activate, and read. The 10 one is the best one, is the green one. Read write, exactly. Good. Now, once I'm done with request 5, as a memory controller scheduler, I go to the queue. I look for any request pending for row 1. Is there any request? No, not in our example. So what do? First come, first serve. First ready now is no longer available. You do first come, first serve. Then simply you go back to request 2 because that's the oldest one as a row conflict. And then I serve. Yeah. Yeah, exactly. Then I serve request 2 and I'm going to suffer 70. Now, once request 2 is opening row 2, what is going to happen? The rest are also row heads, right? So in this case, request 4 is going to be 10. If I had a request 6 that is also targeting row 2, then it will also be 10, right? If you count here the total delay, simply 30, 80, so it's 115, right? So first ready, first come, first serve is giving you a better performance than first come, first serve. The reason is it leverages the fact that once you bring in a row to the row buffer, you can have a lot of hits if you reorder requests before you close that row. Yeah, what is the problem with first ready, first come, first serve? Maybe we ask this earlier question, then we see if there's something better, right? The problem, maybe I should ask you this question as an open thing. What you imagine might be the problem with first ready, first come, first serve, especially if we are in this class wearing the hat of a real-time engineer.
Between the row heads, I don't have any sort of priority.
True, you lack core awareness or priority or criticality awareness. That's correct. Yeah.
So also, I think a lot of tests are coming.
Yeah.
Close, like one other ones that are going to get started.
Excellent point. Yeah, that's really the main problem with first ready, first come, first serve. In reality, if you leave first ready, first come, first serve as is with no control, you realize that the request under analysis might in fact starve completely. There is no bound at all. It's unbounded, right? Why that's the case? Because nothing is preventing new open requests arriving all the time. Here, we stopped at request 5. But what is preventing the CPU that is really sending requests to the memory controller to keep sending open row requests, right? Yeah. Yeah, so let's think of, there are not only 5 requests. This is basically a queue. Once you free in slots, new requests can arrive, right? And those requests take time. By the time I'm done with request 3, for example, which is 10, another request 6, might have arrived, or maybe request 5, because it's still row 1. Another request afterwards might have arrived that's also targeting row 1. And once I'm done with it, another request is arriving for row 1, and another one, another one.
Give a chance for it.
Exactly. So you keep waiting a lot for conflict requests, including the one under analysis, right? And a lot here means theoretically it's unbounded, right? I can really keep waiting forever, right? There is, in fact, research that has been done that people even have used this characteristic of first ready, first come, first serve for what we call denial of service attacks in main memory. What they say is that they use a core to craft a memory pattern that keeps sending a lot of bombarding basically the memory controller with open requests, such that the other core that might be a victim is not able to get serviced at all. Good. And this is doable. This is achievable in modern machines, right? From a real-time angle, first ready, first come, first serve. We have proven in the past, like my group, we proved in the past, like 10 years ago, that in fact, theoretically, there is no bound. You cannot really bound it, right? Which is an easy proof. The intuition is easy, right? Is again, you can keep row heads. Now, yeah. Excellent point. Thank you. That's exactly what really happens even in some of the existing machines, right? What they do is what they call, we have a version of first ready, first come, first serve with a threshold.
Yeah.
Or a cap or a bound. To say, I only allow X number of requests to be reordered. So once you open a row, there is a maximum on the number of requests targeting that row. Once you reach that maximum, you close the row, even if there are other open rows, right? That's really the way you can prevent starvation and do some fairness among cores and also be able to have a bound. Good.
This eventually leads to memory overflow at some point, right? So how it is.
Well, on average case, it doesn't really cause a problem because in average, even if we say theoretically you can start, what really happens in reality is that, well, it's not the case unless it's really a targeted security scenario. On most modern applications, they are not able to push a lot of open requests to the memory controller anyway. So, and this is an observation that you'll find a lot. Average case machines are not really, which are most of our computing machines, they are not designed for the corner cases, right? They basically designed for average case. I mean, if there is a security issue that might happen once every while and going to cost me a ton of money to be able to address, I don't care about it. When people discover it, I will start banning. Right now, it's not cost efficient. So money is the driving factor of the chip market, right? Real-time angle is a bit different because real-time angle, even if it's a very hypothetical corner case, we said previously is that if it's very critical task, that when sequence of failure, you can lose lives. This is why certification puts a lot of emphasis on, well, no, you cannot use first read, come first serve. If you come to me with a memory controller that has first read, come first serve, you are done. There is no certification. Yeah, the cap, as you said, right? Or do first come first serve. In fact, for a very long time, people have used first come first serve for safety critical systems. Memory control. It's not very efficient, but then the cap one was introducing.
So with this cap, you're saying there will be about, what I'm trying to say is that Pro 2 in this example, I know that it will not be delayed more than
A
5.
certain number of frames. Exactly.
And what about the 100 analysis? It's closed or open?
Yeah, your worst case is to assume it is closed,
Yeah.
unless you do some analysis that guarantees to you
That will be open.
it's going to be open. Now, taking this one step further, how can I do this analysis and still guarantee it? Only if you have your own exclusive bank, similar to the cache partitioning case, right? So if we do bank partitioning in the DRAM and you have your own exclusive bank, I can reason about row heads and row conflicts. Other than this, I cannot really reason because other cores can really ruin my own analysis.
So this specific bank, it will be for only one type of request or maybe
One task, for example,
Okay, what?
right? Because you partition per task. What you care about is the task execution time then.
Okay.
Yeah. How much time we are in?
Sure.
Okay. Okay, so I will stop here, okay? Give you, we need, let's say 25 minutes, including the stuff. So we have 10 minutes, basically. You can have a break or you can ask me questions if you would like. And then we must start the quiz 11:50 sharp, right? Because we want to make sure we leave a few minutes at the end to handle stuff. Good. Again, those that want to walk or fresh their mind, go ahead and do this. For those that basically want to ask questions, feel free to ask. Yeah.
Listen, I was actually able to go through all the slides, alhamdulillah.
Good. Alhamdulillah.